All right, final exam review for X chemistry class. Let's take a look at this thing. Science System International Units, factor label conversions, significant digits, uncertainty, accuracy versus precision. Precision, how close measurements are to each other. So you need more than one measurement. Accuracy, how close it is to the true value. So you just need one measurement there. Density, how much matter is in a space. Chemical changes a substance. Physical does not change the actual compound formula. Classification of matter, elements, compounds, pure substances, and mixtures is when you take these and mix them together. So let's take a quick look. Prefix representing the largest value. That would be kilo. Remember, 1 kilo is equal to 1 base unit. So I'm going to just use grams because we can as a base unit. 1 kilo is equal to 1,000 base units. 1 gram then is equal to 100 centigrams, and 1 gram is also equal to 1,000 milligrams. 297 Kelvin. To go from Kelvin to Celsius, we need to subtract 273. 297 minus 273.
It's 24.
And that's going to be 24. Chemical change? Tarnishing of silver, definitely. If we take a look, dissolving sugar in water, we can get the sugar back out by vaporizing off the water. Steam condensing, that's just a phase change from vapor to liquid. Chopping wood, well, you're not changing the wood still has the same chemical structure. The number of significant digits in this number, well, only these are significant. This 0 is significant because it's terminating to the right of the decimal. This 0 is significant because it is between two significant digits. Non-zero digits are always significant. This 0, even though it's to the right of the decimal, it is not terminating, meaning it's not the last thing in the number. 1, 2, 3, 4. So this would be 4. This would be 4 significant digits. The density of ethyl alcohol is this. What is the volume of 3.32 grams of ethyl alcohol? If we look at the density as a conversion factor, this is the easiest. 3.32 grams. Every 0.789 grams is 1 centimeter cubed. 3.32 divided by 0.789.
It's about 4.2078.
So 4.207 is going to round to 4.21. Notice my grams is going to cancel out, and I'm going to end up with centimeters cubed. I'm going to end up with centimeters cubed on that. 2. 3 significant digits, done. The term used to describe how consistently several measurements of some quantity given a similar result is several measurements. That right there tells me that we're talking about precision. How close it is to the true value. That right there is accuracy. Given 1 inch equals 2.54 centimeters, how many centimeters are in 1 yard? 1.00 yards. Every 1 yard is 3 feet. Every 1 foot, keep in mind whatever's up here is going down here, is 12 inches. Every 1 inch is 2.54 centimeters. 1 times 3 times 12 times 2.54.
The answer is 91.44.
91.4 centimeters equals 1.00 yards. Which of the following is numerically correct answer to the problem below and is quoted to the correct number of significant digits? So, 12.37 minus 11.07.
The answer is 1.3.
That's actually 1.30 because they need to go out this many decimal places. Oh, sorry. Just batted this thing. 3.5575 plus 3.520.
It's 7.0775.
7.0775, but it only goes out 3 decimal places. Oh wow, I wasted a bunch of time there, didn't I? I just looked, and this is there's only one significant digit here. It's a 3. So that means that we're just going to have one significant digit. Out of these, it has to be this one. Let's go ahead and see what we get. 1.30 times 3 times 16.58 divided by 7.0775.
The answer is about 9.1362.
I didn't do it for something. No, I did. So it's going to be 9. Done. Express 0.00560 in scientific notation. So 1, 2, 3. So 5.60 times 10 to the negative third. 5.60 times 10 to the negative third right here. We've got to maintain that significant digit there. We generally report a measurement by recording all of the digits and one uncertain digit. How many significant digits are there here? All of them are. So 4 or 5. Using the rules of significant digits, calculate the following. 6.167 plus 83.
It's 89.167.
So we keep all the digits, but we only have 2. 89.167 divided by 5.10.
That would be about 17.4837.
So 17.48 is what our calculator gives us, but we can only have 2 significant digits. Remember, we only round once, so that 4 is below 5, so that 7 remains a 7. Convert this to milligrams. So 5, 6, 8, 7.4 grams. Every 1 gram is 1,000 milligrams. Oh, that's weird. Milligrams. 5,687.4 times 1,000.
That would be 5,687,400.
1, 2, 3, 4, 5, 6. So there we go. E. These don't hold up their significance. Onward to atomic structure. Structures of the atoms. Protons and neutrons make up the nucleus. Electrons are outside of there. Isotopes are when you have the same number of protons, so you are the same element, but you have a different number of neutrons. Carbon 12, carbon 13, carbon 14. Periodic table. Groups go up and down. Periods go across. More metals than nonmetals. Metals are on the left side, nonmetals on the right side. Anything touching that line, except for aluminium and polonium, are considered metalloids or semi-metals or metalloids, or whichever one you prefer. So, the symbol here we have is Ga. So we look on the periodic table, we find Ga, that has 31 protons. Its atomic number is 31. The atomic number always goes below the mass number. 69 minus 31.
It's 38.
That's how we find the number of neutrons. The nucleus has 69 particles. 31 of them are protons. 38 of them are neutrons. We have 3 more positives than negatives. So we have 3 more protons than we do electrons. 31 minus 3.
The answer is 28.
So we have 28 electrons. The atomic number, as we said, is equal to the number of protons. The mass number is up here, that is 69. And the net charge is plus 3, because we have 3 more positives than negatives. What element is 34? That is selenium. (34 plus 46).
It's 80.
So it's selenium 80. Number of electrons. The net charge is 0, so the number of electrons is equal to the number of protons. The atomic number is equal to the number of protons, and the mass number is equal to 34 plus 46, which is 80. A certain atom contains 34 protons, 34 electrons, and 45 neutrons. The atom has a mass number of 34 plus 45?
It's 79.
79. What is the charge of an atom that loses 2 electrons? If you lose 2 electrons, you have 2 more positives than negatives. An ion contains 50, what ion contains 50 protons? So we go for 50 protons, that would be 10, 68 neutrons, and 48 electrons. So it has plus 2 because it has 2 more protons than electrons. 68 plus 50?
It's 118.
So that would be a 10, 118 ion, 2 positive ion. Which one of the following statements about atomic structure is false? The electrons occupy a very large volume compared to the nucleus. That's true. Almost all of the mass of the atom is concentrated in the nucleus. That is true. The protons and neutrons in the nucleus are tightly packed. That is true. The number of protons and neutrons is always the same in a neutral atom. This is not true. The number of protons and electrons would be the same in a neutral atom. So here we have calcium 2 positive. It has 20 protons. This is true. 20 neutrons. This is true. And 18 electrons. Well, this is true. And we found it the first try. 20 protons. 20 plus 20 is 40. So that's the right number of neutrons. 20 minus 2 is 18 electrons. Element 38. Element 38. Element 38. That is in group 2A. So that is an alkaline earth metal. Halogens are in group 7A. Noble gases are in group 8A. Transition metals are often called the B elements. And group 1A is known as the alkali metals. Which of the following is a noble gas? Well, as I said, here they are. Neon is one of these. All of the following are characteristics of metal except. Ductile means you can pull and stretch it out like into wire. Malleable means that it can be hammered. Metal does conduct electricity. This is why they say don't stick a knife into a toaster. This is close. Solids at room temperature. There's only one exception. So I'm going to let that slide. Tend to form anions. That is not true. They don't tend to form anions. They tend to form cations. Metals form cations. They form cations by losing electrons. Names and formulas of compounds. Polyatomic ions, hopefully you have them on the back of your periodic table or a list of them somewhere you need it. Names, formulas, and charges of 10. It's from the summer assignment. You should have them memorized. Differentiate and name formulas of common ionic and covalent compounds. Ionic means it starts with a metal. Covalent means it starts with not a metal. Don't worry about the acids, just make sure you know HCl is hydrochloric acid and H2SO4 is sulfuric acid for now. That's down here somewhere, I'm sure. Writing and balancing equations. We'll get to that in a second. So, is this ionic or covalent? Potassium is a metal. Potassium, that would be potassium bicarbonate or potassium hydrogen carbonate. Either one works. Nickel. Nickel is a metal, so that is ionic. Nickel is also a metal that is not in group 1A. This is an alkali metal, so nickel will require a Roman numeral. So this is nickel oxide. The charge of oxygen is -2. There are 2 nickels to balance that charge of -2, so each of those nickels has a charge of 1. Nitrogen is not a metal, so we use the prefixes dinitrogen pentoxide. Iron. Iron is not in group 1A and 2A, silver, zinc, or aluminum, but it is a metal, so it's ionic. So we're going to need a Roman numeral for this. Iron oxide. In this case, oxygen still has a -2. Wow, all of these oxygens. -2 times 3 is 6. There are 2 of these, so 6 divided by 2 is 3. Iron 3 oxide. Lead oxide. This is ionic. Lead is not in group 1A, 2A, silver, zinc, or aluminum. Oxygen has a -2 charge. There's one of each of these, so it is lead 2 oxide. And last but not least, this is silicon. Silicon is not a metal, it's a metalloid. Remember metalloids, we're still going to use the silicon di, we're going to use the prefixes. We're not going to say monosilicon dioxide because we never put the mono on the first element. Silicon dioxide. Boom. The number of sulfur atoms in the formula aluminium sulfate is, well, sulfur atoms, 3 times 1 is 3. How many oxygens are there? 3 times 4 is 12. How many aluminiums are there? 2. It's always the number that, that's like it. The number refers to what it goes directly after. This number refers to whatever's in the parentheses because it goes directly after the parentheses. So that's like saying we have 3 of these. So how many sulfurs do you have? 3. 1, 2, 3 sets of 4 would be 12 of the other one. So 3 sets of 4 is 12. All right, the pair in which the formula and name are incorrectly matched. So if we take a look here, where the name is incorrectly matched. Okay, so if there is no O, you have to have hydro at the beginning for an acid, and then you change the ending to ic, hydrobromic acid. That's correct. Aluminium hydroxide. That is correct. This is actually nitrate. If it ends in 8, I'm sorry, this is nitrite. If it ends in 8, if this were nitrate, this would be called nitric acid. But if it ends in ite, like the sulfide up here, you change the ending of it to OUS. So it's actually this one. Again, remember, all you need to know is HCl is hydrochloric. And H2SO4 is sulfuric. Sulfuric. That's good enough for now. So don't worry about that if you don't understand that yet. We learn that next semester, actually. Calcium phosphate, CaPO4, and the charge of Ca is +2. The charge of PO4 is -3. So that's going to be 6 for the least common multiple. 6 divided by 2 is 3 calciums. 6 divided by 3 is 2 phosphates. Iron 3 sulfate, FeSO4. Charge of 3 there from the iron by knowing the Roman numeral. And the sulfate has a -2. So again, 6 divided by 3 is 2 Fe's. 6 divided by 2 is 3 SO4s. Aluminium acetate, AlC2H3O2. The charge of acetate is -1. The charge of aluminum is +3. So we need 3 -1s to balance out 1 +3. Copper 1 carbonate, CuCO3. CuCO3, and we actually need 2 of these +1 coppers to balance out the one -2 carbonate. Ammonium sulfide, NH4, that's a +1, that's a -2, so we will need 2 of these NH4s for 1 sulfide, which has a -2 charge. Which of the following formulas is correct? Na2O is good. BaCl is not good. We need a 2 there. CaCl2 is correct. AlCl3 is correct. And EnCl2 is. Okay, cool. So all of them are correct except for this one. So you would need a 2 there. FeSO4. So that is iron. Iron needs a Roman numeral. It's not in group 1A, 2A, silver, zinc, aluminum. That is sulfate. Sulfate has a charge of -2. Since there's only 1 iron there, it must have a charge of 2. Na. Sodium is in group 1A, so it does not need anything. And C2H3O2 is acetate. Potassium is in group 1A. NO2 is nitrate. Ca, that is calcium. OH, calcium is in 2A, so it does not need a Roman numeral. OH is hydroxide. Ni is nickel. Nickel is in group is not in group 1A, 2A, silver, zinc, or aluminum. So that means that it does require a Roman numeral. Since carbonate is -2, nickel would have a charge of 2. Write the correct polyatomic ions and their charges. Obviously, you will always have your periodic table with you, so you won't need to necessarily be able to do this, but these are the ones that you should have memorized, I guess. These are the most commonly used ones. There you go. Onward. Reaction types and predicting products. Recognize the reaction type. Synthesis, things coming together. Decomposition, breaking down. Combustion, hydrocarbon reacting with oxygen to form carbon dioxide and water. Single displacement, one thing comes in and pushes the other out. So you have element, compound, double displacement. The two singles push, the two cations push each other out and replace each other. Alright, so let's take a look then. Write the balanced equation for the following reactions. Sodium metal plus water. So that's going to be, that right there is going to be a, what do you call it? A single displacement. Sodium's going to come and push out one of the hydrogens. So we have NaOH. The hydrogen goes off by itself then. Now we need to do the balancing. Sodium can do this because it is above, let's see, show this real quick. It is above hydrogen in the activity series, and it actually is above the ones that says lithium to sodium will replace hydrogen from acids and water. So it's still one of the ones that can actually do it from water. So, as it does that, we have two hydrogens here, so we need a 2 there. That's going to make us need a 2 there and a 2 there. 2 Na, 4 hydrogens, 2 plus 2 is 4, 2 oxygens, 2 and 2. Good. Then you could go ahead and use your, not activity series, but your solubility thing and see that that is aqueous. And you know that H2 is a gas. This is a liquid. That's a solid. Zinc plus hydrochloric acid. Zinc plus HCl. Zinc does have the ability to push hydrogen out of an acid only. So zinc is here. It does still above hydrogen, so it can push it out of an acid only. So that means zinc's going away with chlorine and hydrogen is going away by itself. We know hydrogen is diatomic, so it's H2. We would also find that that is aqueous if we looked it up. Problem is that zinc has a 2 plus charge and chlorine has a -1 charge. So we need 2 chlorines to do that. So that 2 there and that 2 there means we need a 2 in front of there. That is aqueous and that is solid. Sodium carbonate plus aluminum chloride. Na2CO3 plus AlCl3. Both of these would be aqueous. And this is going to be a double displacement. Aluminum is going to go away with the carbonate. So Al2CO3 3 plus NaCl. To balance this, we're going to need 2 of those and 3 of those. So that means we're going to need 6 NaCl's. This is aqueous. Let's check on the carbonate. So if we take a look here, here's carbonate. Carbonate with lithium, sodium, potassium, rubidium, or cesium, or ammonium is soluble. Aluminum is not in that list, so that is something else entirely, so that is insoluble. So that is going to be solid. Propane plus oxygen, C3H8 plus O2. That is combustion. Combustions always make CO2 plus H2O. If it's complete combustion, we need a 3 there, a 4 here. So that's going to give us 6 plus 4 oxygens, that is 10, so we'll need a 5 there. Magnesium plus oxygen gas, that's 2 elements, so that is going to be a synthesis, and that's going to make magnesium oxide. This is a gas, this is a gas, this is a gas, and this is a gas. This is a solid, this is a gas. This is actually a solid. It's that white powder that you saw from that lab that we did, that I did, I guess I should say. HClO4 plus KOH. So with this, we've got an acid and a base. So what this is going to make, it's going to make a salt and a water. So it's going to make H2O because it's a double displacement, and potassium perchlorate. And potassium perchlorate. And it's balanced. Cool. This would be aqueous, and this would be liquid. Aqueous, aqueous. So, double displacement, synthesis, combustion, double displacement, single displacement, single displacement. Use the activity series to determine whether the following reactions occur. If they do, write the balanced equation. Gold can never replace anything. Gold can never replace anything. So that's not going to be a reaction. Lead. Can lead replace copper? So we go here. Lead is above copper. So lead can replace copper. So we're going to get lead sulfate and copper. Here we have, that should be good, Ki plus Cl2. Ki plus Cl2. Can chlorine replace iodine? Yes, it can. So that's going to be KCl plus I2. We need a 2 there and a 2 there. That's good. Determine the solubility of these using the solubility table. So let's take a look. Ammonium. Anything with ammonium is soluble. So that is aqueous. Anything with potassium is soluble. So that is aqueous. Wow, they did something weird here. Anything with cesium is soluble. So that is aqueous, and that is aqueous. Strontium hydroxide, though, let's check it. Hydroxide with lithium, sodium, potassium, rubidium, cesium, and ammonium, soluble. Strontium isn't one of those, so that is insoluble. So this would be solid. Determine if the double replacement reaction will occur. If so, write the balanced equation. So it's not going to occur here because both of these we're going to get water and something with potassium. So no, it's not going to occur here because we have lithium and ammonium, so they can't make solids. So it will occur here. I guess we could call this one making the water occurring too. Let's do this. AG and AG is going to go with CL. Why did I write AL? AG is with CL. There's going to be 2 of those. Plus, that's going to be solid. Plus calcium and nitrate. Remember, nitrate never makes solids. So we're going to need 2 of those AgNO3s. This one actually would be an acid-base reaction. So you're going to get H2O. That's going to be the liquid. But the other thing you're going to get, this potassium sulfate, that is not going to be insoluble. So that's going to be aqueous. But this liquid forming, I mean, I consider acid-base reactions because they do neutralize the acid and the base at the same time. Write the net ionic equation of the silver nitrate and the sodium chloride from above. So when we do this, we're going to take out anything that we're going to break up this thing so that it is in all the ions for the aqueous stuff. Right? And this is aqueous 2, so calcium 2 plus 2 Cl negatives. All of that stuff aqueous. Oh, I should put a plus right here instead of an arrow. Now that's going to form AgCl, which is solid. We don't break that up on there because it's solid. And the calcium 2 plus 2 NO3 negatives. The NO3s are the same on each side. The calcium is the same on each side. So our final formula for this, the net ionic equation, would be 2Ag plus aqueous plus 2Cl negative aqueous yields 2AgCl solid. Boom. Which of the species in the following complete ionic equation are spectators? So the K is not going to be, it's aqueous in both, so it's the K, and the NO3 are aqueous in both. So K and NO3, right here. K and NO3. What is the coefficient for water when the following equation is balanced? So we have 2As, so we're going to need a 2 there. We have 3SO4, so we're going to need a 3 there. So it gives us 6 oxygens here. So it looks like we're going to need 6. Here we have 3 times 2 plus 3 times 2, so that's 12 hydrogen. So yep, it's going to be 6. Onward to moles. Do I have enough time? Yeah, I should have enough time. 10 minutes, 12 minutes, yeah. Moles, atoms, and Avogadro's number. Remember, Avogadro's number is 6.02 times 10 to the 23rd. The molar mass you find from the periodic table, you add those things up. Percent by mass is the part divided by the whole times 100. Empirical formula is the most reduced formula. Stoichiometry is using a balanced equation. The limiting reagent is the one that is used up first. So I think I am going to rest right here for a second. All right, so let's take a look. How many grams does 4 moles of H2O weigh? So we start with 4 moles of H2O. Every 1 mole has a mass of 2 times hydrogen, 1.01, plus 16. So that's 18.02 grams. Moles cancel out. We're left with grams. 4 times 18.02.
It's 72.08.
72.0. calculate the mass of 7.55 times 10 to the 20th atoms of cobalt. 7.55 times 10 to the 20th atoms. Every 6.02 times 10 to the 20th atoms. Since it says atoms, we know we're using Avogadro's number, is 1 mole. And cobalt, every 1 mole of cobalt, look at the periodic table, weighs 58.93 grams. So, in the calculator, 7.55 second, and then the E, 20, divided by 6.02 times 10, oh, hit the wrong button there, times 10 to the 20th, times 58.93. We get 7 actually it's, let me check, make sure I did this right. Ah, look at that, 6.02 times 10 to the 23rd. I feel a little silly about that one. And then we get 0.00739. E. How many grams of potassium are in 12.5 grams of potassium chromate? So we need to find the percentage of potassium in this chemical formula. So if we take potassium is 39.10, chromium is 52, and oxygen is 16. 7 times 16 plus 39.10 times 2 plus 52.
It's 242.2.
The total mass of that would be 242.20. The amount of potassium, 39.10 times 2.
It's 78.2.
78.20 divided by 242.2 times 100.
That would be about 32.2873.
So that's the percent, 32.29% potassium. So that means out of 100 grams of this, 32.29 would be potassium. So 12.5 grams of that every 100 grams is 32.29 grams of potassium. 12.5 times 32.29 divided by 100.
The answer is about 4.0362.
4.04 grams. Ammonium carbonate contains what percent of nitrogen by mass? Oh, fun little problem here. It wants us to basically know the formula. NH4 2CO3. So we need to find the part that is nitrogen, which would be 28.02. We're going to divide that by this whole thing. 8 times 1.01 plus 28.02 plus 12.01 plus 3 times 16.
It's 96.11.
96.11 times 100. 28.02 divided by 96.11 times 100.
The answer is about 29.154.
So 29.154, that's going to be 29.2. Calculate the molar mass of ammonium sulfate. NH4, 2SO3, and Mg3PO4, 2. Wow. All right. 3 times 16 plus 32.06 plus 8 times 1.01 plus 2 times 14.01.
The answer is 116.16.
116.16. 2 nitrogen. 8 hydrogen. 1 sulfur. 3 oxygen. Yep. 3 times 24.31 plus 2 times 30.97 plus 8 times 16.
The answer is 262.87.
262.87. The empirical formula of a compound that is 40% sulfur and 60% oxygen is. So we got to change that percent to grams of sulfur and that percent to grams of oxygen. Every 32.06 grams of sulfur is 1 mole of sulfur, and every 16 grams of oxygen is 1 mole of oxygen. 40 divided by 32.06.
It's about 1.2476.
60 divided by 16.
The answer is 3.75.
3.75 divided by 1.25.
That would be 3.
So it's a 1 of these sulfurs to 3 oxygen. SO3. An unknown compound contains 1.19 grams of nitrogen and 3.41 grams of oxygen. What is its empirical formula? We're going to do exactly the same thing. 1.19 divided by 14.01.
It's about 0.08493.
3.41 divided by 16.
It's about 0.2131.
0.213125 divided by 0.0494.
It's about 4.3142.
I said it wrong. 0.213125 divided by 0.08494.
That would be about 2.5091.
So it's 1 nitrogen to 2.5 oxygen, but we can't leave it like that. So that's going to be multiplied by 2 nitrogen to 5 oxygen. A compound with the empirical formula CH2 has a molecular mass of 56.12. So we're going to take that molecular mass and we're going to divide it by the empirical mass, which is 14.03. 56 divided by 14.
It's 4.
So that equals 4. So that means we multiply the C by 4 and the 2H by 4. So that's C4H8. What percentage of nitrogen is in nickel 2 nitrate? So let's add that up. Nickel is going to be 28.02. We're going to divide that by the total. 58.71 plus 28.02 plus 6 times 16. Oh. 58.71 plus 28.02 plus 6 times 16.
The answer is 182.73.
28.02 divided by 182.73 times 100.
The answer is about 15.334.
So that's 15.3%. 3 moles of ammonia contain how many molecules of ammonia? 3 moles. Every 1 mole is 6.02 times 10 to the 23rd molecules. So I think it's going to be 3 times 6, which is 1.81. But let's go ahead. I'll show you how to put it in the calculator real quick. 3 times 6.02 times 10 to the 23rd, 18.01, 1.81 times 10 to the 24th. How many grams of phosphorus are needed to produce 25 grams of tetraphosphorus decoxide according to this equation? So, 25 grams of P4O10. Every so many grams of P4O10 is 1 mole of P4O10. And from the equation, every 1 mole of P4 O10 requires 4 moles of phosphorus, and every 1 mole of phosphorus is 30.97 grams of phosphorus. 4 times 30.97 plus 10 times 16.
It's 283.88.
25 divided by 283.88 times 4 times 30.97.
It's about 10.9095.
10.9 grams, it looks like. Hydrogen gas and oxygen gas react to form water. H2 plus O2 yields H2O. There's 2 of these and 2 of those. How many moles of water will form if 4 moles of hydrogen and 4 moles of oxygen are combined in a container? 4 moles of hydrogen and 4 moles of oxygen. Every 2 moles of hydrogen can make 2 moles of water. Every 1 mole of oxygen can make 2 moles of water. So that equals 4 moles of water. That equals 8 moles of water. We can only make the lowest amount, so that would be 4 moles of water. Suppose the reaction calcium phosphate plus sulfuric acid yields calcium sulfate plus phosphoric acid. It's carried out, started with 103 grams of calcium phosphate and 75 grams of sulfuric acid. So I'm going to put that down here so I have some room. 103 grams calcium phosphate, 75 grams of sulfuric acid. Grams of calcium phosphate, grams of sulfuric acid. Every 1 mole calcium phosphate, one mole of sulfuric acid. So, from the balanced equation, every 1 mole of calcium phosphate we're trying to find out how much phosphoric acid will be produced. Every 1 mole of calcium phosphate makes 2 moles of phosphoric acid. And for the H2SO4, every 3 moles of that H2SO4 will make 2 moles of H3PO4. We're trying to find grams, so every 1 mole of H3PO4, 1 mole of H3PO4 is so many grams of it. 30.97 plus 4 times 16 plus 3.03.
That would be 98.
98. 3 times 40.08 plus 8 times 16 plus 2 times 30.97.
It's 310.18.
4 times 16 plus 2.02 plus 32.06.
The answer is 98.08.
103 divided by 310.18 times 2 times 98.
It's about 65.0847.
75 divided by 98.08 times 2 divided by 3 times 98.
The answer is about 49.9592.
So out of these two, this is the lowest. So that means that we're going to be able to make 50 grams. When 12.0 grams of hydrogen react with 12 grams of chlorine, 11.1 grams of hydrogen chloride are recovered. Alright, so we've got to sit here and do this problem up here. I got the room, I think. 12 gram H2, 12 gram Cl2. Every 2.02 grams is 1 mole of H2. Every 1 mole of H2 makes 2 moles of HCl. And every 1 mole of HCl is 36.46 grams of HCl. 35.45 times 2.
The answer is 70.9.
Every 1 mole makes 2 moles of HCl. 1 mole of HCl is 36.46 grams. 12 divided by 2.02 times 2 times 36.46.
It's about 433.1881.
433.18. 12 divided by 70.90 times 2 times 36.46.
That would be about 12.3418.
So we have 12.34 as the lowest out of those. So that's how many grams we have for our theoretical. And here is our actual. So it's actual divided by theoretical times 100. 11.1 divided by 12.34.
It's about 0.8995.
And we times that by 100, we get 89.9%. Calculate the amount of phosphine that can be prepared when 10 grams of calcium phosphide reacts with excess water. 10.0 grams of C3P2. Every so many grams of that is 1 mole of that. And every 1 mole of that, sorry about that, every 1 mole of that makes 2 moles of phosphine. And every 1 mole of phosphine is so many grams. 3.03 plus 30.97.
It's 34.
3 times 40.08 plus 2 times 30.97.
It's 182.18.
10 divided by 182.18 times 2 times 34.
The answer is about 3.7325.
So it's going to give us 3.73 grams of phosphine. When 125.0 grams of ethane burns in oxygen to give carbon dioxide, how many grams of carbon dioxide is formed? C2H4 plus O2 yields CO2 plus H2O. 2 there, so 2 there, 4 there, so 2 there. That gives us 4 plus 2, which is 6. So, 125 grams of ethane. Every so many grams of ethane, or I'm sorry, ethylene, is so many moles of ethylene. And every 1 mole of ethylene makes 2 moles of carbon dioxide. And every 1 mole of carbon dioxide 32 plus 12.01
That would be 44.01.
is 44.01 grams. 2 times 12.01 plus 4.04?
It's 28.06.
8.06. 125 divided by 28.06 times 2 times 44.01?
It's about 392.1062.
That's the best answer. Let's make sure I didn't make any mistakes. Where would I have to go with this? 392.2. Probably a mistake in the, like a small mistake in the molar masses. Whoever got this answer, because I believe mine are right. A 14-gram sample of lithium is reacted with 15 grams of fluorine to form lithium fluoride. After the reaction is complete, what will be present? Oof, all right. They want us to go all out for this. F2 plus Li yields LiF. There's 2 of those, so we need 2 of those. 15 grams Li. Every so many grams Li, 6.94 grams Li, will be 1 mole of Li. Every 2 moles of Li will, we'll make 2 moles of LiF. And every 1 mole, oh, we don't have to go to grams, so we can stop there because it only needs to go to moles. 15 divided by 6.94.
That would be about 2.1613.
2.16 moles of LiF if we base it off the lithium. 15 grams of fluorine. Every 19 times 2.
It's 38.
Every 38 grams of fluorine is 1 mole. Every 1 mole of fluorine makes 2 moles of LiF. 15 divided by 38 times 2.
It's about 0.7894.
Oh, 0.789 moles of lithium fluoride is definitely less than this. So it's not that, because this is our limiting reagent. We know that some is going to be left. Let's go backwards and find the number of moles of lithium left. So to do that, we know that this is existent, and every 2 moles of lithium is 2 moles of lithium fluoride is 2 moles of lithium. So that is 0.789 moles of lithium will be needed. Right? So then 15 divided by 6.94.
The answer is about 2.1613.
So 2.16 moles of lithium are there. 2.16 minus 0.789.
The answer is 1.371.
So that's how much lithium we would need to use to make this much lithium fluoride. We started with 2.16. We subtract that, we get 1.37. What a fun problem. All right, the gas laws. Boyle's law, that is volume and pressure. Charles's law is temperature and volume, and the Gay-Lussac's law would be pressure and temperature, but they all fit together into the combined gas law. Now for this, kinetic molecular theory would be applicable, and Dalton's law of partial pressure. STP conditions, and that's it. So let's do what we can here. You wouldn't need to know that. Wouldn't need to know that. The gas is collected by water displacement. Okay, probably this one. The barometric pressure is 99.3 kilopascal, and the partial pressure due to water vapor pressure is 3.3. What is the pressure of the gas? Well, you just take that minus that. because you didn't even have to look at the chart because I gave it to you. So that would be 96.0. Which of the following gases would have, nope, at standard conditions, what mass of, nope, a gas occupies, here we go, a gas occupies 525 centimeters cubed at 25 degrees Celsius and 81.5 kilopascal. Its volume at STP is what? So that is 273.15 for T2. And since our kilopascals, it's 101.3, I believe, kilopascals. So we need to solve for V2. So P1 V1 over T1 equals P2 V2 over T2. T2 goes up here. P2 goes down here. We cancel out on this side. So temperature 2 up. 25 plus 273.15.
The answer is 298.15.
All right. So let's see if I can do all this. 273.15 times 81.5 times 525 divided by 101.3 divided by 298.15.
It's about 386.9669.
So we would be looking at the 388 here. They probably didn't use the 0.15. Let's try that real quick, just for fun. 273 times 81.5 times 525 divided by 298 divided by 101.3.
The answer is about 386.9491.
387. Oh, there we go. Maybe they used 101 instead of 101.3 or something like that. All right, so let's take a look then. It says calculate the number of kilograms that can be compressed to the volume. Again, we're not there yet. A sample of nitrogen gas, we're not there yet. A gas has a volume of this, this, and this. What is the temperature of the gas? Okay, so this is a combined gas law problem. So here is V1, P1, T1. Here is V2, P2. So we're solving for T2. So T2 goes up to the top, and all this is equal to P2, V2. So T1 goes up, T2 goes up, P1 and V1 both go down. So let's see if I can do it. 640 times 198 times 288 divided by 760 divided by 175.
The answer is about 274.4012.
So that's 274 Kelvin. It says container A and B have equal volumes at the same temperature and pressure. A is filled with helium and B is filled with argon. What is true about the containers of the gases? If they are at the same temperature and same pressure, and they have equal volumes, then they will contain the same number of particles. Because even though if they're two different chemicals, helium and argon, the distance between those particles is greater than the size of the particles themselves. That's it. You should be ready, by doing this, you should be ready for the 9 weeks test.